The heating and cooling sources of a building can be categorized into three levels according to the plant location. A package terminal heat pump, for example, is a local system commonly used in hotels. It packages heating, cooling, and ventilation components into a ductless, convenient all-in-one unit. In a central system, the heating and cooling sources are located in the central area of the building, from which heating and/or cooling are delivered to thermal zones by ductwork and/or by piping. This type of system can service either small-scale buildings such as a house or large-scale buildings such as a multi-story commercial building. In a district system, cooling and heating capacities are provided by an energy plant off-site through a network of underground pipes. The energy plant typically serves multiple buildings within a particular service area, the district. We will focus on the local and central levels in this course, which involve generating cooling and heating media on site. Vapor compression refrigeration cycle is based on the principle that a liquid expanding into gas absorbs heat. The cycle contains four major components: compressor, condenser, expansion device, and evaporator. Refrigerant, for example Freon, is piped in this enclosed cycle. Compressor compresses refrigerant from low pressure, low temperature vapor to high temperature, high pressure vapor. High pressure, high temperature vapor refrigerant rejects heat in condenser and becomes high pressure, high temperature liquid. Expansion valve removes pressure from the liquid refrigerant to allow expansion or change of state from a liquid to a vapor in the evaporator. Low pressure, low temperature liquid refrigerant absorbs heat in evaporator and becomes low pressure, low temperature vapor. In this cycle, the condensing side is in high temperature and high pressure, whereas the evaporating side is in low temperature and low pressure. Heat is pumped from the cold side to the hot side. This diagram shows the relationship between the refrigeration cycle and the building. The refrigeration cycle can be used to provide cooling if air is blown into the interior through the cold evaporator. If this cycle only cools the building as shown in this diagram, where the refrigerant flows clockwise, it is called an air conditioner. The refrigerant flow can be reversed in the winter, and the condenser and evaporator switch. Now the indoor fan blows air through the hot condenser and it provides heating for the building. If the device operates in both cooling and heating modes in different seasons, by switching the refrigerant flow, it is called a heat pump. A direct expansion DX system cools the air that directly passes through the evaporator in the refrigeration cycle. The keyword here is air. The air will then be delivered to the interior to cool the spaces. In general, DX is less expensive to install than chiller systems. A chilled water system cools the water that passes through the evaporator. The keyword here is water. The chilled water then forms a chilled water loop with a coil to allow air to pass through to cool the spaces. Large commercial buildings often use chilled water systems as they are more cost-effective in operation and require less maintenance than DX systems. In this design, we call this equipment that contains the refrigeration cycle a chiller, and this equipment that contains the chilled water coil and hot water coil for heating, a fan and filters, an air handling unit. In the chiller, the condenser needs to be cooled to keep the device working properly. In the system shown in this diagram, the condenser is cooled by air. We call this an air-cooled chiller. The air handling unit can be located indoor or outdoor, whereas the air-cooled chiller is typically located outside due to the need of moving a large amount of air through the condensing coil. In this design, a water loop and a cooling tower are used to cool the condenser. We call this a water-cooled chiller. The cooling tower is a heat exchanger that lowers the temperature of the water that in turn cools the condenser in the chiller. The cooling tower is typically located outside due to the need of accessing a large amount of air, whereas the water-cooled chiller can be located either inside or outside. Water-cooled chiller systems are more efficient than air-cooled ones, but they are more expensive in initial installation. A gas furnace uses a gas burner as a heat exchanger to heat the air passing through. The heated air is then delivered to the building for space heating. The furnace can be integrated with an evaporator coil for cooling in cooling seasons. The evaporator is connected with the outdoor condenser unit by refrigerant lines. A heat pump can also heat a space in its heating mode, with the outside coil as the evaporator and the indoor coil as the condenser. Retained air from the space is warmed up by going through the condenser and then supplied back to the space. Heat pump is generally used for heating in locations with mild winters due to its low efficiency in extended subfreezing conditions. This is a typical central air system in which a chiller and a boiler supply chilled water and hot water to the air handling unit. Air runs through the air handling unit, either cooled or heated, then being delivered to the space as supply air through the air ducts. Return air travels from occupied spaces back to an air handling unit, either in ducts or in open ceiling plenums. This diagram shows a system with plenum return, where the entire ceiling volume serves as the return channel. This diagram shows duct return, where retained air is sent back to the air handling unit through return ducts. A major advantage of a ceiling return plenum is that it is less expensive to install than duct return because less ductwork is required. Compared to plenum return, a major advantage of duct return is that it improves air quality. Underfloor air distribution (UFAD) uses an open plenum space between the concrete floor and a raised access floor to deliver the conditioned air directly into the occupied spaces. Air is delivered upward through supply outlets located in the floor and returned through the ceiling plenum. UFAD only conditions the lower 6 feet of the space where occupants reside, thus having the potential to reduce the chiller and fan energy's consumption. Wires, cables, and piping can also be accommodated in the floor plenum. These features provide great flexibilities in future renovations. The main disadvantage of UFAD are higher initial cost and lack of familiarity in the building industry. A thermal zone is a space or a collection of spaces having similar space conditioning requirements, the same heating and cooling set points, controlled by one thermostat. Manufacturers drive the division of thermal zones such as orientation, space function, budget, etc. We can use this example to illustrate the approaches to thermal zoning. This diagram shows the first design. Each corner computer lab is placed on a separate thermal zone for its orientation and function. A bank of 6 offices facing north is placed on one thermal zone. Zone 6 and 7 each includes 3 offices facing west and east. Internal spaces with no exterior walls or windows are on one thermal zone. The entire south-facing open office is placed on one zone. This is an improved design in which the south-facing open office is further divided into 3 separate zones. The north-facing bank of offices are also further divided up into 2 zones, each including 3 offices. With more thermal zones, this design will improve thermal comfort, but it will increase cost. Single-zone systems include a single plant and distribution system serving one thermal zone, which is controlled by one thermostat. They may heat or cool or both. This two-story single-family house is served by a single-zone system because the entire house is controlled by one thermostat. The system includes a central air distribution system with a moderate set of ducts. This is another example of a single-zone system, where each zone of this one-story commercial building is served by a packaged rooftop unit on the roof. In multi-zone systems, a set of plant and distribution systems serves more than one zone. Mixing or damper devices are used to modulate either air volume or air temperature or both to meet the requirements of different zones. This house has two thermal zones, one on each floor. The two thermostats control the dampers in the ducts to modulate the air volume to each floor so that different thermal loads can be met. This two-level building is divided into multiple thermal zones served by one set of air handling unit and chiller. Air is distributed from the air handling unit to different floors by vertical ducts and to different areas on a floor by horizontal ducts. Controlled by the thermostat in each zone, a damper box modulates the amount of air being sent to a zone to meet the thermal needs in the space.